A particle constrained to move along x-axis in the domain x lies between 0 and L has a wave function psi x is equal to sin n by x by L, where n is an integer. Normalize the wave function and evaluate the expectation value of its momentum. And the condition for normalization is, the general condition for normalization is, if n is the normalization constant, then n square within the limit minus infinity to plus infinity psi square theta is equal to 1. This is the general condition for normalization. Here we are considering a one-dimensional wave function psi x, and this the integral limit will be 0 to L. So the equation will be the wave function, that is the normalization constant n square integral 0 to L psi x psi star x dx equal to 1. Normalization condition, or it can be represented as psi x square dx equal to 1. That is n square integral 0 to L psi is sin nx, psi x is sin n by x by L. Therefore the psi x star, it will be, or psi square x, that is sin square n by x by L. Then the equation is n square sin square n by x by L into dx equal to 1. This sin square can be represented in terms of cos theta, that is sin n by x by L is equal to, or sin square n by x by L is 1 minus cos 2 n by x by L, and we can just integrate, that is n square into integral 0 to L 1 minus cos 2 n by x by L whole raised to by 2 into dx equal to 1. So this integral can be divided into two terms, integral 1 by 2 into dx minus integral minus cos 2n by x by L by 2 into dx. So the second term, cos 2n integral 0 to L cos 2n by x by L into dx will be 0, because the integral of cos 2n by x by will be sin 2n by x by L, and when the limit will becomes L, then it will becomes sin 2 pi, the multiple of 2 pi will, then sin 2 pi multiple will be 0. So this term can be neglected. So the remaining equation is, that is n square 1 by 2 into integral 0 to L dx, 1 by 2 into integral 0 to L dx, that is L by 2. L by 2 is equal to 1. Therefore, the normalization constant n can be written as root of 2 by L. Root of 2 by L. Then the normalized wave function is, root of 2 by L into sin n by x by L. Normalized wave function, and evaluate the expectation value of its momentum. The expectation value can be generally represented, that is for an variable function a and its operator is a operator, then the expectation value can be represented as psi. Expectation value is equal to integral psi, then a operator psi star a operator psi theta divided by integral psi star theta. But for normalized wave function this will be 1. For normalized wave function this will be 1. Hence this is 1. It is the expectation value of a dynamic variable A can be written as integral psi star, integral minus infinity to plus infinity psi star, the A operator psi d2. Here it is we are considering in one dimension the momentum operator, so it is considered as the px, one dimension px, x component only, is equal to, here the limit is 0 to L, then psi star, the operator of the momentum is minus IH cut dou by dou x into psi dx. It is the expectation value of the momentum. Integral 0 to L psi star, momentum operator minus IH cut dou by dou x psi dx. It will give, that is minus IH cut will be taken outside, minus IH cut integral 0 to L. This psi star, a normalized function, is root of 2 by L into sine n by x by L. Then that is the root of 2 by L the whole square. It will give 2 by L. 2 by L sine n by x by L dou by dou x of sine n by x by L into dx. Then 2 by L, that is minus IH cut 2 by L, and this dou by dou x of sine n by x by L, this will give cos n pi x by L into n pi by L. That is the n pi by L will be taken outside, n pi by L. The remaining one is 0 to L sine n pi x by L. This will be cos n pi x by L into dx. This will give, that is minus IH cut into 2 by L n pi by L integral 0 to L. This is sin theta cos theta. That is, we have the relation sin 2 theta is equal to 2 sin theta cos theta, or sin theta cos theta is equal to sin 2 theta by 2. Sin theta cos theta is equal to sin 2 theta by 2. This is sin theta cos theta. That is sin 2 theta by 2. That is sin 2 n pi x by L to dx divided by 2. By 2 will be taken outside. This 2 and 2 will cancel. This will be n square. Then it will be minus IH cut n pi by L square integral 0 to L sin 2 n pi x by L into dx, and this value is 0. Value is 0. That is the expectation value of the momentum is 0. And the next problem is determine the de Broglie wavelength of an electron which is accelerated through a potential difference of 100 volt. Determine the de Broglie wavelength of an electron which is accelerated through a potential difference of 100 volt. Generally, the equation for the de Broglie wavelength of a charged particle which is accelerated through a potential difference V, and if E is the charge of that particle, then we can represent the equation, the energy as, the kinetic energy as E is equal to EV, where is the charge of the electron and V is the potential difference applied. In the case of the de Broglie wavelength, lambda is equal to h by mv or h by p, but the p can be written as in terms of the kinetic energy, that is p square by 2m is the energy. So, or p can be written as root of 2me, or here the E will be root of 2m into EV. Energy will be EV. So the equation will becomes, that is lambda is equal to h divided by root of 2m EV, and substituting these values, h is 6.634 into 10 is to minus 34 divided by root of 2 into mass of electron 9.1 into 10 raised to minus 31, and the electron charge is 1.6 into 10 raised to minus 19. The potential applied is, it is 100 volt, 100, and this will give us the value. It is about 1.23 into 10 raised to minus 10 meter, or it is 1.23 Armstrong. This is the de Broglie wavelength. Next problem is calculate the maximum wavelength that hydrogen in its ground state can absorb. What would be the next maximum wavelength? Calculate the maximum wavelength that hydrogen in its ground state can absorb. What would be the next maximum wavelength? So according to we have the equation, general equation is equal to h nu, or is equal to hc by lambda. We are looking this equation, energy and lambda. That is, lambda is equal to hc by E. That is, the maximum wavelength means the energy will be minimum. The maximum wavelength means the energy will be minimum. So calculate the maximum wavelength that hydrogen in its ground state can absorb. So the energy will be minimum. The energy will be minimum. The energy will be minimum means the energy we are considering, the energy we know that the energy, the transition will take place from the ground state to the first excited state. From the ground state to the first excited state. That is, the energy will be minimum. So we know that the energy of the ground state is, the energy of ground state is minus 13.6 eV. Energy of the ground state is minus 13.6 eV. And energy of the first excited state is, energy of the first excited state is minus 13.6 by 2 square. That is, for the first excited state, for the ground state, n is equal to 1. For the first excited state, n is equal to 2. That is 2 square is equal to minus 13.6 by 4, and that will be minus 3.4 eV. And similarly, the energy for the n is equal to 3 state, the energy for n is equal to 3, that is minus 13.6 by 3 square. It is minus 13.6 by 9. It will give minus 1.5 eV. That is, energy for n is equal to 1 state minus 13.6. Energy for n is equal to 2 state minus 3.4 eV. And the energy for the third state is minus 1.5 eV. Then the maximum wavelength corresponds to the energy from the ground state to the first state. That is, this minus 13.6 and 3.4 eV. That is, the maximum energy takes place. That is minus 3.4 eV minus 13.6 eV. And the maximum wavelength correspond to the energy. We can consider the maximum wavelength, maximum lambda wavelength corresponds to energy, that is, the energy will be from the ground state to the first excited state. That is minus 3.4 eV minus 13.6 eV. That is 13.6 eV. That is, this will give 10.2 eV. 10.2 eV. 10.2 eV. That is, the corresponding, the maximum wavelength will be, the maximum wavelength lambda is equal to, that is hc by, that is energy is equal to, we can write that is energy difference, that is E2 minus E1 is equal to h nu, or hc by lambda. Therefore lambda is equal to hc divided by E2 minus E1. Lambda is equal to E2 minus E1. That is, we can write the expression for the equations, the values 6.634 into 10 raised to minus 34 into 3 into 10 raised to 8 divided by this E2 minus E1 is 10.2 EV, 10.2 EV, 10.2 into 1.6 into 10 raised to minus 90, and this will give approximately 122 nanometer. This will give approximately 122 nanometer. So the question is, what would be the next maximum wavelength? For the next maximum wavelength corresponds to a jump from ground state to the second state. That is, from ground state to second state. This requires the corresponding energy will be, for the ground state to the second energy state, the energy will be, energy is equal to 13.6 minus 1.4, because this is the energy 1.4. That is minus 1.5 EV minus 13.6. That is 13.6 minus 1.5 EV. That will give 1.21 EV. 1.21 EV. The corresponding wavelength lambda is equal to HC divided by this E3 minus E1. Here it is E3 minus E1. That is 6.634 into 10 raised to minus 34 into 3 into 10 raised to 8 divided by E3 minus E4. It will give 1.21. 1.21. It is electron volt converting into joule. 1.6 into 10 raised to minus 19 joule. And this will give value 103 nanometer. 103 nanometer. So the maximum wavelength, that is corresponds to the first maximum wavelength is 122 nanometer and the second most is 103 nanometer.